The objective of this video is to develop the mathematical model and control architecture for centralized control of a magnetically levitated shaft. Specifically, this video is going to focus on developing the 4 degree of freedom rigid body model. We're not worried about gyroscopic effects in this video, that will be saved for a later video. Instead, we're just going to focus on how we can control force in 2 planes on a shaft in order to control the shaft's tilting and radial movement. And so to kick this off, I've added a couple rather complicated diagrams here of our system. So let's start with the top row. So first I'm introducing our coordinate system. You can see that we've got an x hat unit vector pointing vertically and a z hat unit vector pointing horizontally. Y hat vector is coming out of the page at us. And on this, I've defined angles. I've got an angle alpha, an angle beta, and an angle theta. And each of these angles is defined so that when you look down the unit vector, so if you stand here and look down, you see the angle rotating in the counterclockwise direction. So angles are positive in the counterclockwise direction when you stare down an axis. So see here we're looking down the y-hat axis, and we see beta in the counterclockwise direction. Same in the z-axis if we were to look this way. Okay, now on the left side, I've drawn a magnetically levitated shaft. So in gray, this long gray thick line is our shaft. And then on this shaft, I've labeled our angles. So here again, we've got the z-hat direction going this way, and we've got the x-hat direction coming up out of the page at us. Going vertical, and y-hat is coming out of the page at us. And so I've got angles labeled around our shaft. So the rotation of our shaft is defined as theta. The deflection of our shaft in the counterclockwise direction along the y-axis is labeled as beta. And the net deflection of our shaft in the x direction is labeled as x0. In addition to that, I'm labeling over here and over here where our magnetic bearings are located, or our bearingless motors. So specifically, I've put a dot in the center of these regions to indicate where forces are produced. So on the right side, we've got a dot here, and then Fx2 is labeled above it. On the left side, we've got a dot here, and Fx1 is labeled above it. And then at each of these dots, I've labeled our displacement. So nominally, our shaft would be on the z-axis, but this is a displaced shaft. In fact, it's been displaced both in the beta angle and in the x-hat direction. So we've lifted our shaft up in the x-hat direction, and then we've rotated it by beta radians. And so we can observe what that means in the air gap of each of these machines by in the air gap of each magnetic bearing or each bearingless motor as the deflection of delta x2 and delta x1. Okay, also we've got feedback sensors, and our feedback sensors are targeted on these small dots here, and they're measuring a distance x1 and a distance x2. And so this is all related. x2 is related to delta x2, is related to delta x1, related to x1 by our state variables of x0 and the rotational angle beta. And then I've labeled how far our magnetic bearing actuators are located from the center of the shaft. So that's r delta. And then how far our sensors are located from the center of the shaft, which is rs. Okay, so that is the shaft drawn in this plane. Now we're going to rotate this system 90 degrees so that our y-hat unit vector points vertically, and now our x-hat unit vector is into the page. And if we do that, we have the following angles. These are the same angle definitions. They all rotate counterclockwise when you look down the unit vector. But you'll notice that alpha is now pointed down in the page, and that's because we're standing on the opposite end of our x-hat unit vector. X-hat unit vector is going into the page, whereas up here it was coming up straight, and up here y-hat was coming out of the page. So pay attention to this difference of the angle label, it matters. And now we've again drawn our shaft over here. So y-hat is pointing up, z-hat is going off to the side, and you can see this shaft is again deflected in the net direction by y0, and it's been rotated by alpha radians. Okay, so this is just depicting the situation that we're going to be studying in this video. We're now going to be developing differential equations for x0, beta, y0, and alpha. and then using that to get transfer functions for how each of these degrees of freedom, each of these state variables, depends on the forces that we produce with our magnetic bearing or a bearingless motor. So here I've listed our state variables, which are the variables that we've been talking about up above. And the first thing to note is that we want to be able to calculate what our state variables are based on measurements. So our position sensors are again measuring this distance x2, x1, and I didn't label it on here, but also a y2 and a y1. And we need to convert that into our state variables. And so we can see that x1 is going to be equal to x0 minus rs times sine of beta. We can just do trigonometry about this line that forms here, over here. And it gives us this expression. And if we use a small angle approximation, we can get this into a linear form. And we want this in a linear form because we're doing linear control. And we can do a similar thing for x2. And so finally we can write out an expression for x0 and beta. And we can do the same thing for y1, y2, and alpha, and we would get the same results. Well, we get the same results for y0, but we get a negative of that result for alpha. And that's just because of the way that the angle is defined up here. Alpha appears this way. That is, if we start from the beginning, we would have this expression. All right, so next we're going to use the equation of motion. We're going to use the equation of motion combined with our linearized force model to get transfer functions for x0, y0, alpha, and beta. So if we start with x0, we see that the total force acting in the x direction is going to be fx2 plus fx1, and force is equal to mass times acceleration, and so we get this differential equation. And we can do the same thing for torque to get a differential equation for beta. So the torque acting at node 1 and node 2, we sum them up, and we get this differential equation. And we can approximate the torque acting upon our shaft in the beta, so as to move it in the beta direction, as being the lever arm of the force at this point times lever arm, and the force at this point times lever arm. And the lever arm distance is this r delta. And notice the sign here. A positive force at fx1 is actually going to accelerate the shaft in the opposite direction as beta is oriented. And we can do the same thing for the alpha direction, only now our sign is again reversed. And so we can take these equations and we can combine them with our linearized force model to get our transfer functions, or first to get our complete differential equations and then our transfer functions. And the linearized force model, as you'll recall, is this equation that the force is equal to a kf times a current plus k delta times our delta displacement. And for this model, we're going to modify it slightly. We're going to say that we have k delta by 2 times our displacement. And we're doing that to reflect that we have a total k delta, which is when we have both magnetic bearings acting at the same time. So we split k delta between the two magnetic bearing units. It makes the math come out a little bit cleaner later. And just like we did before, we're going to replace this kf I1 and I2 with FC. We're going to define an FC so we can replace that. Okay, and so we could have done the same thing for the y direction. We have the same equation form. So if we do all of this, we can now write out our differential equations. And so what we've done here is we've recognized that this quantity right here is just equal to x0. And you can see that from this expression right here. We derived it for x1 and x2, but we could have also done this for delta x1 and delta x2. And then we can do the same thing in the y direction. Okay, so now we have our two differential equations for the net radial force in the x and y direction. And we'll do the same thing in the angular directions, in the beta and alpha directions. And so we can get this expression for beta. And this equation for the for the alpha direction. And so again, to do this, we took this expression here and we plugged tau beta 1. We plugged this in for tau beta 1, and this in for tau beta 2, this for tau alpha 1, and this for tau alpha 2. And that's how we arrived at these two differential equations that we then plugged in our force model to get this expression and worked the math until we had these expressions. So at this point, we've got these this set of four differential equations, and we can see that this is a MIMO system, a multiple input, multiple output. We input in our states or our measurements of delta x1. Actually, I'm sorry. Our measurements are this x1, x2, y1, y2, and our inputs to the system are FC x1 and x2, FC y1 and y2, and everything is kind of coupled together, right? We got these differential equations that depend on each other. But we can transform it into four single input, single output systems, and we like to do that because then we can go back to our simple block representation and use our classical control design techniques. So I'll show you how we can do that. Basically, we define these quantities fx sum, fx diff, fy sum, and fy diff. And so if we use these equations, we can note that we have an fx diff here, and an fcy diff here, an fx sum here, and an fy sum here. We'll plug in these new relations, and then we'll write this as a set of transfer functions. And so here's our first transfer function. We've got our differential equation here. We've turned into a Laplace equation, and then we've solved for x0 over fcx sum. And doing that, we get this very familiar transfer function. In fact, this is the same transfer function that we had when we were looking at the 2 degree of freedom model. And that means that it has the same unstable right half plane pole at this 1 over the mechanical time constant. So I've added a subscript m here to indicate that this mechanical time constant is related to the mass. And so we can write out these same expressions for the y0 direction, and you won't be surprised to see that we get the exact same transfer function. And so in the angular direction, we get another transfer function that's of the same form as our mass transfer function, but has a different mechanical time constant. So we still get an unstable pole at the mechanical time constant, but now the mechanical time constant depends on the moment of inertia about the beta axis in the beta direction. And we can drive the same thing in the alpha direction. Okay, so we now have our transfer functions. We have two transfer functions that are each reused twice. So we either have this GPM or GPJ. And our job is to design controllers to stabilize these systems. So we have four systems to control, 4 state variables to control. That's x0, y0, beta, and alpha. But we actually only need to design 2 controllers. We're going to have 4 controllers total, but 2 of those controllers will be acting on the GPM transfer function, and 2 will be acting on the GPJ transfer function. And we already know how to design these controllers. We talked about it in the previous video on decentralized control. These plants have the same form as the plants in that video, so the same control design approach can work. You can also talk about more sophisticated digital control too, or simpler controls such as proportional derivative control as well. But the point is that we have constructed our system as a set of as a model which has similar transfer functions as we previously discussed. So now with this more elaborate system, we still reduce it down to a set of decoupled systems that we know how to design controllers for. And finally, I want to sketch out the control architecture and how this looks in implementation. So you've got a reference for x0, and then you have your measurements of x1 and x2. And from these measurements, you have to calculate your x0 state and your beta state. And so right here, I've put on the screen how we go from x1, x2 to x0 and beta. And this is coming straight from the very beginning of the lecture up here. We're just implementing these expressions. And then at this point, we're comparing it to a reference for x0 and our reference for beta. And we're going to feed this into our regulators for the 2 transfer functions. So this is our regulator for the mass transfer function. That was this case up here, the x0 and y0 states. And here's our regulator for the angular transfer function. And these give us our force references, but they come in the form of FCX sum and FCX difference. So we have to convert back from FCX diff and FCX sum into the FCX1 and FCX2 so we know what currents we need to regulate. And then we can convert those forces into currents using our force current gain, which we talked about up here. So at this point, the steps depend on whether you're doing a bearingless motor or a magnetic bearing, but regardless, you feed it into some kind of current regulator, which is then going to deliver voltages to the terminals of your machine. So that is the control architecture. And we can also sketch the model that we would use for designing our controllers. And so finally you get these 2 block diagrams. And so notice that I've indicated that you have a different set of gains for your mass controller versus your angular position controller. Otherwise, the general structure is the same. So, in summary, this video has set up the 4 degree of freedom rigid body model. That was the set of diagrams that we drew here and the accompanying equations. And we've also talked about centralized control without using the word centralized control much. But basically, we're controlling all degrees of freedom of this, all 4 degrees of freedom, with the 4 actuators. I apologize, 2 actuators, but each actuator can actuate in the X and the Y direction. And we set up our model of this with 4 state variables and 4 measurements. We showed how to convert from the measurements to the state variables. We then derived the differential equations for each state variable, and notice that they are coupled because of their dependence on x1 and x2. We then showed how we can decouple the equations with this transformation, and we arrived at a set of 4 differential equations, but actually 2 unique differential equations. So two differential equations are both this GPM form and the others are this GPJ form. And we recognize that these differential equations, or these transfer functions, are actually in the same form as we discussed in a previous video, and so we already know an approach to design controllers for them based on the values that we have for R delta and K delta, and tau m and tau j. Next, we sketched the general control architecture for the complete 4 degree of freedom centralized control approach.